advice I got is attend, for job hunting, one of the pieces of advice that I got was attend as many user groups as you can. And since Russ was here and I was here, why don't you show up for lunch?
Howdy. Sorry, we got talking and I forgot to get the meeting started quite as same time as I normally do. Okay. And let me get Anna to start the recording.
Yeah, looks good in top left.
Is it? Okay, we got it. All right. Okay, let's see. I've got to do both of these roles today. As long as the camera doesn't freak out, we're good to go. Okay. Hi, folks, and welcome to the June Northwest C++ Users Group meeting. Apologies to the folks online. I got the recording started, or got the meeting started just a little bit later. We are recording as we normally do, so we just don't, they start the recording now automatically, so I don't have to remember to do that. We are going to change the format just a tweak. So what I'm going to do, just so you guys know, I'm the presenter today as well. But we are going to do a little 5-minute prefix, which I've got slides for now, and then we'll go into the presentation. So the first 5 minutes will be a little more formal. First off, we'd like to thank our sponsors, primarily Microsoft at this point, for letting us use the reactor room and our Microsoft Teams support. Part of that, Microsoft does have a code of conduct. So we'd like everyone to please follow the code of conduct. It's pretty straightforward, you know, be respectful and, you know, don't be obnoxious and stuff like that. I don't know, do people want a couple seconds to read that slide or is everybody comfy with it?
A couple seconds isn't going to help without my distance glasses.
If I can make it bigger or not. No, I can't when I'm in presentation mode. That's okay. You behave yourself anyway.
What is the recall feature later?
Say again?
What is the recall feature later?
Okay. Okay. And we do have a few announcements at this point. C++ conferences. Hey, Chris, it looks like you made it. Do you want to handle this one?
Okay. Yeah. Call for volunteers is open. The call for talks for meeting C++, which is in Berlin, is open for a couple more days. The CPP Con tomorrow is the last day for the early bird. If you wait past tomorrow, you have to pay an extra $400. So buy now. And there is a refund period that if you want to get a discount or decide you can't go, you can cancel. Check it out on the CPPCon website. Also coming up here in a couple of weeks is CPP North in Toronto, which is actually south of us. But so it's not that far north. There's still slots available to attend. And there's a hotel discount ends in the next couple of days. I'm not sure on the exact paperwork on that. But so if you want to come, make your reservation there quick. I just got back from Norway, and it turns out while I was there, I found out I'm also going back to Norway in September, right before CPPCon. I'm going to be speaking at NCD Tech Town. So I'm excited for that. Of the NCD conferences, it's the more C++ one. So back to you, Lloyd.
Okay, thanks, Chris. And by the way, Chris, if you got any conference news that you want to get to me, just get it to me ahead of the meeting, and I'll get it in the slides. We'll update these slides and announcements every month now. So,
yeah.
Okay. Future NWCPP meetings, August 15th, we're going to do something a little different. I still need to get the reservations, so don't get too set on this yet. It might change slightly. We're going to do a pizza social. So there's a park called Grass Lawn Park just up the road here. And we're going to go rent out their picnic shelter and we'll get some pizza in. And rather than doing a presentation, we'll just do a pizza social. So we won't have a presenter per se, but it'll be kind of trying to recapture some of that just personal interaction, chit chat that we used to have before the meetings. Sorry for hybrid folks, that will be an in-person only event. Yeah, we don't quite have drones to deliver pizza yet, although we have talked about it. September 19th, that meeting will be also a little bit different. Every year we start trying to do a lightning round. So that'll be short 5-10 minute talks. So if you want to talk on something, and it doesn't have to be strictly C++, anything computer related is fair game. It's just show up, bring your laptop, we'll plug you in and we'll go from there. If we end up with dead time, we'll start a debate like East Coast or East Const or West Const or something like that and make it fun that way. October 17th, I am looking for a speaker. So again, if anybody would like to do a full-on presentation, please let me know. Again, it does not have to be strictly C++. I think a lot of our talks lately have kind of migrated into that. In the past, we've had other languages. We used to have a speaker talk about Haskell quite a bit. We've had Walter's done many talks on D. We've had quantum in here a couple of times. We had one on the BBC microbit at one point. So, feel free to expand. It's as I look through our schedule for the last year or two, we've been getting into a little bit of I wouldn't call it rut, but narrower pattern. So in the next year or so, I'll be kind of looking to push that back out again. Okay. With that, we'll start moving into our feature presentation. Apologies, it's me again, me tonight, so I'll be talking for the whole time. I do have a whole bunch of slides, so try to hold questions till the end of the presentation. Keep the questions short and focused so everyone gets time to interact. And try not to interrupt the speaker when other members are speaking. Kind of ties in with our code of conduct thing. Okay, so with that. Okay, CUDA without a PhD. Okay, and I should have kept something to drink. Oh well, I'll live. Okay, so here's the.
I'll get you something.
Oh, don't worry about it. It's probably better I don't actually, especially if it's caffeinated. We'll get through the slides faster, however. Okay, so basically this is kind of an overview of what we'll go through tonight. Just a quick show of hands or people on. How many people are generally familiar with GPU computing and CUDA as a concept? Okay. Reasonably. Okay, that kind of gives me an idea of how to balance the talk a little bit. Okay, we'll go through what is CUDA. CUDA, how to set up CUDA on a Windows machine. I'm going to set up a problem definition. So we're actually going to solve I wouldn't call it a real world problem, but a moderately interesting example program or problem. We'll do it as a single threaded solution on the CPU. Then we'll switch it into the GPU world and show how those relate. And then we'll talk about debugging, resources, and Q&A. Okay, so quick disclaimer. CUDA is a very deep topic. If you've gotten into it, there are people who spend their whole careers, basically doing CUDA optimizations, and you can really, really get into this, right? To get the maximum performance from a GPU-based application, you need correct formulation. You have to consider the hardware, the data access patterns, memory bandwidth, processor topology, and that just kind of starts. This talk is about none of that. Sorry. There's a lot of good talks if you really want to get into it. I was telling a few people before the official meeting started. Yeah, I took a little bit of a sabbatical last summer and kind of got into this. And what I found is the gap was there's not anything to really get somebody started quickly, right? So what this talk is about is how in very short order you can get up to speed, and I'm talking a couple hours type of thing, right? Get up to speed, move a particular data pattern, a particular application pattern onto the GPU, and get a reasonable speed up out of it. It's basically get your foot in the water, get started, get something that's meaningful, and thank you. Folks, if you're not on mute, please mute your microphones. Thanks. And so anyway, basically, basically get your foot in and get something productive done, and then grow from there, right? Okay, so GPU architecture. A modern CPU consists of a small number of complex processors. They're mostly independent of one another, not considering cache overlap or cache coherency issues and things like that. And they generally perform independent tasks. So every processor is kind of doing its own thing, right? The computational pattern for that, most people in this group probably know this, is SISD, single instruction, single data. That's kind of the classical, you've got one instruction stream, one data stream, and you blend them together and off you go. A modern GPU consists of hundreds to thousands of very simple processors, and they perform the same operation on multiple pieces of data at the same time. Okay, this is it's kind of like vector processing on the CPU, but much more so, right? That pattern is typically referred to as SIMD, single instruction, multiple data. And NVIDIA takes a little bit of a twist on that. They call theirs single instruction, multiple thread. And the difference there is the later GPUs do not require each core to be on exactly the same instruction. Okay, there's some constraints around that, and I'm not fully versed on exactly what those are. But if you have an if statement, for instance, what they used to do is, if you had an if then else, so a true clause and a false clause, both processors would execute both data streams or both instruction streams, and they would just mask out the appropriate one. Single instruction, single thread actually allows them to do this a bit and execute the right one. And there's some limitations on that, and I'm not quite sure exactly how they pull that back together at the end. But that's the difference between SIMD and SIMT. The GPU also likes to work in 32-bit floating point. Integer is also supported. 64-bit is there, but it's not quite as efficient. So you take a pretty good performance hit for 64 on most processors. And I'm not going to talk about the they also have, especially if you get into like the H100 or A100, there's also these more optimized floating point formats. Yeah, F8, F16, F1. Yeah, I'm not going to talk about those either. So most everything we're going to do today is 32-bit floating point and 32-bit integers supported equally well. It's natively a 32-bit processor. Okay, so from this description, we get an effective speed up in the following case, right? So this is the general use case of when do you want to use a GPU over some other architecture. You have a very large data set, or a set of data that needs to be processed. I should actually look this way so the camera can see me. So think hundreds of megabytes to gigabytes worth of data, right? So large data sets. The data format is regular. It's typically stored in arrays or vectors. Okay. Keep in mind, GPUs really came about for doing graphics, right? So you've got a 2D array of pixels, right? That's kind of its natural working environment. You need to do the same or very similar operations on each element. The operations to be performed on each element are all independent. In other words, you do not have data dependencies between the elements, right? So you can break it up and have each processor work on something independently. And the amount of work to be performed on each element is significant enough to justify copying the data at least twice. So we'll get to that one in a second. Let's talk about the CPU memory architecture, or GPU memory architecture. A typical GPU contains a dedicated bank of memory that's independent from the normal CPU memory. It's typically called device memory. The GPU memory is optimized for highly parallel access patterns. So access bus widths on this thing tend to start about 192 bits wide. And if you go into the upper end, 4096 bits wide is also possible. So very parallel access patterns. The caches are also optimized for very parallel patterns.
Are they like what used to be called vector registers?
No, totally different.
Why?
Don't have the full detail on that. Okay, anyway, if you're going to process information on the GPU, it first has to be copied from the CPU memory into the GPU memory. Those of us who are a little older remember paged memory and specialized device memory. It's basically like that. So anything you're going to do on the GPU, you have to amortize that cost of copying onto and off of the GPU memory. You can also use the data directly on the GPU, right? You don't have to copy it back and then copy it over. If you've got a chain of operations, you can put your input data onto the GPU memory, do all of your operations, and then pull it back. Anyway, that takes time, right? There's also things called unified memory, shared memory, texture memory. These are very specific memory architectures on the chip. They all have special uses. I'm not going to get into any of that at the moment. That's a little more deep detail. Okay, what is NVIDIA CUDA? CUDA is a framework and a set of tools that allow for application development that runs on the NVIDIA GPU hardware. Yes?
Sorry to interrupt. What does CUDA stand for?
I have no idea. It's the thing that runs on the GPU.
Compute and unified in the an architecture.
Yeah. Yeah, I've just always called it CUDA. Good question. The main components are the NVIDIA compiler, which is called NVGCC, the CUDA API. There's a set of debugging and profiling.
Unified device, you have it there. Oh, no, somebody commented.
Yeah. Okay. We've got debugging and profiling tools. Those are called Nsight Compute. There's a set of math libraries, and a lot of these are going to be familiar. There's a CU BLAST, basic linear algebra system, FFT library, random number generator, a tensor library, sparse matrix, a solver, JPEG, thrust, and a whole bunch of other ones. There's also a set of technologies, the most common of which is called GPU direct storage. That essentially allows the GPU to load data directly from disk. So that's primarily for gaming, right? If you're going to load a bunch of textures and graphics, you just suck it in directly to disk, don't even go through main memory. But for us, if we're not doing gaming, we can load our data that way too. Okay, CUDA setup requirements. So CUDA can run in Windows and Linux environments. I don't think it's fully supported on Mac any longer. And it can also run on the ARM hardware through the NVIDIA Jetson platform. So these are little small computers that you can get for $100 to $1,500, depending. And they're designed for embedded applications. We were talking about robotics at the beginning. Robotics folks tend to use the Jetson platforms quite a bit. For this exercise, I'm going to use the following configuration. This is not a minimum recommended configuration. It just happens to be what I've got. From time to time, I do some high-end computing, which is why I'm into this. But we're going to talk about some benchmarks a little bit later, so you should know what I'm running against. An AMD Ryzen 9 7950X. It's a 16-core, 32-thread processor. I think it's actually AMD's most modern at the moment for a desktop. Motherboard's an Asus. 64 gigs of DDR5 4800 RAM. The key component here is a GeForce RTX 4080 with 16 gigs of RAM. For folks who follow this stuff, that's like the second one down from the top. It's not like the top end, which tends to be really, really spendy, but it's pretty good. Yeah, they're enormous. Yeah. And by the way, they use a lot of power.
Yeah, see, that's not on there.
Yeah, you notice I didn't mention my power supply. That's a whole nother story. Windows 11 Pro 62-bit. We're going to do this in Visual Studio Community Edition 2022, and running CUDA 12.2.
Sorry to interrupt again. Do you know if this will also work with VS Code? A lot of people use VS Code instead of VS Community Edition.
Yes, it will.
It's the editor. It's just the
Yeah.
editor.
Oh no. Yeah, it will work. But the simple method I'm going to show for getting everything going, you'll have to do a little more customization. So yeah, VS Code will work. Obviously, if you're on Linux, you're not going to run Visual Studio. So to keep this super simple, I put together a really simple tool chain, right? And this is about the simplest thing you can do. Basically, load up Visual Studio Community Edition, and there's the link. When you load it, configure for at least C++ development, whatever else you want. Then you just install the NVIDIA CUDA for Microsoft Visual Studio. There's the link for it. Basically, you do 2 installs and you're set to go. If you're going to use VS Code or any other type of editor, what you'll end up doing is installing your tool chain, be that Visual Studio, GCC, whatever, and then you're going to install the NVIDIA tools beside it, and then you're going to have to hook up and do all that type of stuff. So it will work. It's just not this simple.
Is there anything particular about the community edition versus other editions? So,
Yeah, you don't have to pay for it.
okay.
Okay, I should have said simple and cheap, except for the GPU card. Okay. Yeah.
I'm sorry, maybe we'll get to this later. When you deploy your code, is there a subset of the tools that's just a runtime, some runtime libraries that you need to?
It basically builds it all into the executable. So when you deploy the final package, right?
So all you need is that whoever runs it needs to have compatible hardware.
Yeah, you have to have compatible hardware, and as far as I know, I don't know if it pulls any dependencies with it or not. I think it all sits in the EXE.
Okay. No, not like the old days when you had to deploy
Yeah.
MSRP, CRT, all of that stuff.
Yeah. Now, if you're running in Visual, if you're running in Visual Studio, you're going to have to deploy its runtime package as well, right?
Right, but nothing on top.
But I don't think there's anything for the CUDA stuff that you need to do. I think it pulls it all in.
All right.
At least that's what I've seen. I'm sure there's different ways to do it with more advanced. So this is the sample problem we're going to get into, and I'm going to speed up a little bit because I've got a lot of slides to go through in about, oh no, we got about an hour and a half. We're good till, okay, sorry, moving along faster. Anyway, sample problem definition. We're going to take a fairly simple problem that's got a moderate amount of work to it. It's a little bit academic, but it'll illustrate what we're doing pretty directly. Basically, we're going to take we're going to compute the hypotenuse of a large quantity of triangles, given the lengths of the triangles, or the lengths of the sides of the triangles are in 2 vectors. Okay. So everybody remembers the good old Pythagorean theorem. H equals the square root of a squared plus b squared, right? Putting it in that form. We're going to take two vectors of random numbers, call them a and b, and then we're basically just going to apply this formula to them. So we've got three vectors that we're working with, two inputs, one output. This is a little arbitrary, but, you know, squaring things, adding them, and then taking the square root, that's a little bit of work, and it's, you know, reasonably more than a couple of copies. So it matches our problem definition. What we're going to do is we're going to do this on the CPU, and then we're going to move it to the GPU, and then we'll compare. For this example, we're going to use 32-bit floating point. Okay, so this is the other reason I went with Visual Studio instead of Visual Studio Code. It comes with the nice little macros and project generators for you. So again, super simple. You can do all this yourself. Basically just fire up Visual Studio, say create a new project. Oh, that's interesting. There's a delay between my Mac and the screen. Basically, then you'll say you want to do a CUDA 12.2 runtime. So that's the project type. Fill in the everything you want for your project. Basically, give it a name, a location, and a solution name. It's all pretty typical Visual Studio stuff. And it's going to give you this nice little project. This is just the standard that comes with the, you know, the sample project, right? I did trim this down a little bit. We'll take a quick look at this though, because we're going to follow somewhat of this general form. And I'll go over this in a little more detail. At the top, you've got a couple of includes. So include CUDA runtime.h, kind of would expect that. Device launch parameters, that's just another one. Standard IO.h, that's just kind of your standard headers. Add with CUDA, this is a kernel. We'll talk about that a little bit more later, but briefly, the kernel function, right, or subroutine, that's what gets pushed as code to the GPU. So you've got 1,000 processors, you're going to have 1,000 instances of that little function running in parallel. Okay, so that's kind of the key execution piece. You get a main, we all know what that is. And they basically kind of do the same thing we're going to do, except I'm going to gut this a fair amount. They just create a couple of vectors and add them in parallel and then go for it. But that, you know, fundamentally, that's the skeleton of a program overall.
Does that get compiled by CL.exe or by NVCC.exe?
We'll talk about that one in a minute. The quick answer is both. Okay, the other thing you need to know is when you're adding code to your project, you don't do like the normal C file, header file, or C++ class. You need to select the CUDA files. And by doing this kind of addresses your question, that is the flag, and you notice they have different headers. It's CCUH for the header file and CU for the C++ file. Those are the tags to the build system to say, these are special for CUDA. That does not necessarily mean they're restricted to CUDA. So CUDA is essentially a preprocessor type of thing. So it will preprocess, strip out its tags, and pass the rest of the C code on to, in this case, MSVC, right? So just by saying, hey, I'm going to do CUDA, you're not restricted to that. It just means send this through the preprocessor, strip out the CUDA stuff and do your special stuff with NVCC with the CUDA stuff, and send the rest of it on down the chain. Okay, this is the single-threaded application. What I'm going to do is I'm going to create a little C++ class to hold all of our data and algorithms. I call that CUDA worker. Let's see. A little bit small. Basically, we're going to use a library called Thrust. I'll talk about that in a minute. That helps with memory management. You notice I'm making about, I think that's 100 million or so, elements in my vectors. Okay. And then it's basically just a straight up class. I've got a constructor and a destructor. I'm disabling the special member functions. I have a function called CPU compute that will perform the hypotenuse or Pythagorean theorem using the CPU. I've got one called GPU compute that will do the same thing in a fully parallel fashion on the GPU. I've got one called verify that will grab the data from the CPU, data from the GPU, and make sure the answer is the same. Don't normally need a verify, but how many folks have worked with floating point units across platform before? How many people have discovered that one floating point unit is not quite identical to another floating point unit? Yeah.
Earlier this week.
Yeah. Guess what? The GPU is slightly different than the math processing on the GPU is slightly different than the math processing on the CPU, as one would expect. It's got slightly different goals. Most of the time it doesn't matter. Sometimes it does. Okay, let's see. The last part I want to take a little bit closer look at. So CUDA has a library called Thrust. And this is a C++ template library. It's based on std vector. The special thing about Thrust is it works for both the host and device memory. So it's basically just a header only include. So you include those headers, host vector and device vector. You're good to go. Guess what host vector does? Yeah, it's basically std vector on the CPU memory. Device vector is essentially std vector on the GPU memory. Okay, so what I do is I create an A, a B, a CPU result, and I've got a GPU result on the host.
Sorry. Oh, is it device or hybrid? Because I suppose if you're just pushing elements one by one, it doesn't make sense to push it from the CPU memory into the.
Right, yeah.
It does a little bit of.
Oh, no, it does a lot more than that. It actually does full DMA transfers between host and device.
But in some optimized fashion.
Very optimized and optimized at the hardware level. And to take that one step further, I talked about unified memory at the beginning. Unified memory is essentially doing the same thing, but it takes the MMU and has the MMU do page swapping between the two. I could have written this presentation using the unified memory, but I want to show A, you have two memories, B, you have to copy, here's how you have to do it, and the unified memory just makes all that hidden for you. Which if you're trying to optimize stuff, you really should know what's going on under the covers. Okay, anyway, on the GPU, we're just going to create three vectors. I call them device A, device B, and device result. Okay, kind of just nomenclature to let me know that, hey, this is on the device. Okay, the constructor is really simple. I pre-allocate memory for the vectors, basically the reserve. I fill them up with a bunch of random numbers. And then this last part is kind of interesting. You notice all I do is say device A equals A, device B equals B, and then I say reserve the result. This is the magic of Thrust. All I have to do is say vector equals vector, and all of the work of copying from the host memory to the device memory, ensuring and handling all the errors, and synchronizing and making sure that you don't go on before that vector or that copy is done, is all handled for you right there. You can do this with the API directly. It's about half a dozen lines of code. It's not hard. This is super easy. Okay, CPU compute consists of basically a loop that calls a common math routine for each set of data. So it shouldn't be anything complicated to this group. It's a for loop. The one thing I do a little bit different, and you'll see why I do this in a minute, is rather than just using the data directly, I set it up with pointers to index my data. That's a pattern that will become obvious why I did it in a little bit. You don't have to do that, but it'll make my example a little better, a little easier to understand in a bit. And basically, one of the things that's very helpful in the pattern I'm presenting here is to do your work, have your worker in a independent function, right? So this is where your question comes in. Where does this thing get compiled? So if you look, I've got a couple of tags in here that are not normal C++, underscore device, underscore device, underscore host. These are tags to the NVIDIA compiler. They tell the compiler where and how to instantiate this function. In this case, I'm saying instantiate on both the device and the host. So this code will get passed to NVCC and MSVC and compiled for both architectures. You don't have to do it that way. This particular case, I'm doing it that way. There's also one more called underscore global underscore, and we'll talk about that one in a minute. Okay, and of course now we need a main. Again, this is pretty straightforward. Header files, I map some namespaces in, mostly to do some benchmarking. So I'm just pulling in the chrono high resolution clock and duration if you support things. Pull in my CUDA worker.h. I've got GPU.h. I'll talk about that in just a second. And then the main function. This particular main function actually has both operations in it, CPU and GPU. Essentially what I do is I do the CPU compute, I do the GPU compute, I time them, and then down at the end I verify them and say, hey, the answers match or they don't. Not exactly rocket science. Okay, now let's convert this to massively parallel. Okay, everybody with me so far? I haven't done anything super obtuse. So, okay. First thing I do is I have this class I call GPU. And this is basically a singleton class, and it just manages the GPU. There are more complicated ways to do this. Again, keeping it simple. I've got one GPU in the system. You can have more. And then you have to manage which data goes to which one, right? Just keep it simple, one. And essentially, what this class does, the constructor initializes the GPU, and then I provide a bunch of metrics for the GPU. We'll talk about that in a little bit more detail. The GPU is initialized with this line right. My mouse is a little jumpy on me. There, CUDA set device, default GPU. That's all you have to do to initialize the GPU. Under the covers, CUDA does a whole lot of work. It's going to go find the GPU. It's going to map the memory into the memory space. It's going to set up all the communications. It's going to initialize the runtime libraries. Lots of stuff. One call. The CUDA API basically gives you a CUDA status for every operation that you do. So CUDA set device is part of the CUDA API. And this is just the pattern that you call CUDA calls with. It returns a result code. You check the result code for success. And if something didn't succeed, you go on. Just to give you an idea of the thrust, what the thrust library is doing under the covers, there's a call CUDA memcopy, right? And you basically copy from host memory to device memory or vice versa. You follow the same pattern. So this little block of make an API call, check the result code, if then else. That's what you would normally do in place of that equal statement. The next thing I do is I just print out a bunch of stats about the processor. We'll get into this a little bit more later. We're not going to get super deep into it. There's warps, there's blocks, there's number of streaming multiprocessors, and basically there's a lot of magic that happens. If you really want to optimize your problem, making your problem geometry fit your hardware geometry is one of the things you really have to work at. We're not going to go that deep in it. The key piece is to know there is a hardware geometry, right? Thousands of cores are arranged in blocks that are abstracted up to basically a 3D matrix that makes it easy to work with. But there's a lot more going on under the covers. Okay. What I'm printing out here is compute capability, major and minor version numbers. That tells you fundamentally what operations are available for your device. It's basically version number of the hardware in the library. And if you're going to run, in this particular example, I'm only running on one GPU. I'm not doing anything fancy with it, so this will run on non-4X series GPUs. But if you can take advantage of, like, say, certain texture memory features or something, that's how you detect it's by this compute capability number. The multiprocessor count, that will tell you, how many processors you've got. That turns out to be a very useful number. The max threads per multiprocessor is a very useful number. And then the max threads per block. Those numbers all tell you kind of bounding and how you want to. We've got a linear array, and what we're going to do is just chop it up, right? We'll see in a minute how those tell us how to chop it up. If you really get into this, there's a data structure underneath this that's yay long. There's probably 50 or 100 different parameters in there you can go after. Okay, the destructor just cleans it up, and that's a CUDA device reset. That's all you have to do. You technically don't need to call this, but if you don't call it and you try to run the profiler's not going to know when things ended and died, and it's going to give you strange things.
Does this imply that you can only have one device using the GPU at a time? So I could see like a game running at the same time you were trying to run your program, and I would imagine a CUDA device reset would break the game if it were happening.
No, actually, so I have not played with that yet. So the models I've messed with, it's one program, one device. However, what's really happening under the covers, so like in this case, I was running Windows, right? The Windows GUI takes advantage of the GPU. So I actually do have the OS and my program going after the same GPU at the same time.
And the OS doesn't crash when you finish your program.
Even though it's Windows. No, I didn't say that. And this, apparently the API keeps track of all of this on a per device basis. If you really get into this stuff, the other thing you can do, you don't necessarily just have to have one computational model running on the GPU at a time. You can build whole networks of these things and store those networks. And that's a whole layer of stuff I haven't gotten into yet, is how you decompose, like, take, for example, an application that's a self-driving car, right? You've got multiple camera streams coming in. You've got multiple object detection streams coming in. You've got obstacle detection and avoidance. You've got path planning, and probably 3 or 4 other things I'm forgetting about, right? All these end up, I've seen architectural diagrams of this. All these things end up as little CUDA processes running around, and CUDA orchestrates that too, including synchronization of data transfer between those things and reallocation of resources on the fly to optimize runtime of those things. Yeah.
The back end of things like TensorFlow or
And-
PyTorch.
And pulling all that, yeah.
The back end of that schedules the execution graph of your
Yes.
neural net.
Yep.
This entire.
In about 10 years, I'll do one of these CUDA with a PhD and I'll talk about that. Yes.
So are you going to explain why is it that you pass the parameters and pointers to the parameters?
Yep, I'll get to that in just a second. Okay, anyway, CUDA device reset just cleans things up. Okay, the GPU is massively parallel. We've already mentioned that. The block of code that runs on the GPU is called a kernel. An instance of the kernel is run on each core of the processor as an independent thread. Okay, so I kind of alluded to this earlier, that little function. CUDA replicates that and instantiates it on every little piece of hardware and keeps track of it. From the developer's point of view, the kernel is just a function call. Under the covers, there's a lot going on. One of the things that's going on under the covers is every one of those function calls, in addition to whatever you pass into it, it gets passed in a set of parameters called a thread address. So the function knows the stuff you pass to it. It also knows where it lives in the world. The easy way to think about this is imagine you've got a grid, right? And the thread address is simply 11 or 00, 01, 02, and so forth. So you get the address of the instance that you're running on. Okay, that's going to become important in a second. Getting your mind wrapped around going from a linear addressing scheme like we're used to in C and C++ to this two-dimensional thread address where things are happening in parallel, that takes a little bit of work to get your mind wrapped around. The easy way, or at least the way I came across to think about it, is the typical way you process like a video game, for instance, right? These things started out as pixel shaders, right? That's kind of where it came from. Every pixel gets its own processor, right? So every pixel that you're going to render gets a little kernel that decides and works out what color that pixel should be. Okay, that's the easy way to, at least for me, to think about it. If you want to play with this and practice that concept, there's a website called shadertoy.com. And if we have time at the end, I can bring it up. Well, actually, I can't because it won't run on this computer. But what ShaderToy does is it basically gives you a playground to play with GPU shaders or pixel shaders, right? And it presents this thread address, and you can make really simple little patterns of, take this thread address and map it to your, a blue gradient. Take this thread address, map it to a red gradient, and now you've got a nice two-dimensional gradient, right? That's an easy way to get your mind over this hurdle. For the current problem, this is a little simpler. We just have basically three vectors of data. They're all aligned, right? They're all the same size. So we're just simply going to chop that up, and two inputs and one output go to each kernel. How do we do that? Let's see. Sure I've got the right one. Yep, this is how we do that. Okay. This little formula right here is how we do that. So the first thing we do is figure out how many threads are we going to run, right? Okay. And the maximum number of threads we can run is basically the max threads per block. Remember that little CPU class I had, or excuse me, GPU class I had? Yeah, you just grab that from the hardware. It'll tell you that number. And it's typically something like 1024 or something like that, right? Okay, how many blocks do we need? Well, we just take our vector size, divide by the number of threads, and add 1. Okay, that gives us a simple ceiling function. Okay, now does anybody notice a potential problem with that? Keep that +1 in mind. We'll come back to it. Okay, next thing we're going to do is call the Pythagorean kernel. This less than, parameter, comma parameter, greater than, is another one of these CUDA language extensions. What that means is launch the Pythagorean kernel on the GPU with the geometry specified by the number of blocks and number of threads. So let's make this really simple for a second. Let's say I wanted to launch something with 100 threads, right? I could just say Pythagorean kernel, num blocks is equal to 1, num threads is 100, right? That's going to give me 100 instances of that thing. What the blocking factor does is basically under the covers, CUDA chops this stuff up into blocks of threads so that it can interleave different processes and all kinds of things. So a block corresponds to a execution unit and hardware control unit on the GPU, right? So one block has enough hardware to control X number of threads, right? And that's what the max threads per block is, right? How big is that piece of control hardware, essentially? I'm simplifying this, but if you get into the docs, they start talking about warps and other stuff. I'm simplifying this, okay? And what it will do is you take your entire array, right? We've got, I don't know, I said 100,000 or something like that, right? Which I obviously don't have that many processors, right? And I've chopped them up into blocks. And what CUDA will do is it will allocate an entire block at a time to that hardware. And if it needs to do it more than once, it will. It just puts them all in a queue and, okay, here's a block, you do 1,000. Or I think it's actually, yeah, you do 1,000. Here's a block, you do 1,000, 1,024, I should say. And it just keeps doing that until it gets through all the work. So this is the mechanism whereby the CUDA hardware and the library chop your big problem up into little pieces and map it to the hardware geometry.
Graphs. It's interesting you don't have divisioning map. So modulo division, it will find the offset in the data for you.
Actually, you'll see that in a second. You actually do have to do that.
Oh, you do?
Mm-hmm. Yep, we just haven't got there.
Right there, you're passing. You know that get, right?
Yep.
Or that's just to initialize it.
Yeah, that's initializing it. So basically what I'm passing in, so this is the first part is describing the geometry and number of threads I want to start. You notice I pass the entire array, the two inputs and the output array, I pass the entire array to every single kernel. Okay? We'll come back to that. Okay. Next thing you do is CUDA get last error. That's just the error handling. Did I successfully launch the kernel? And then there's a CUDA device synchronize. So I just sent a whole bunch of work off to this GPU, right? It's going to go do it. I'm now free to do whatever I want, right? Now, this is a very simple example, but this is my time to go do whatever I want. This is almost like an async type call, right? Mm-hmm. The GPU is going to go off and asynchronously just deal with it. My CPU is doing nothing at this point. And eventually, I want to, think of it as I'd launched 2 threads, right? Eventually, I want to join them back together. That's what CUDA device synchronize is. It's like, wait for all the wait for all the GPU to get done before I move on and try to use the results. So when the kernel launch is asynchronous non-blocking, right? CUDA device synchronize is blocking. Okay, key points there. And again, you notice I do CUDA success. If, we'll talk about this a little bit with debugging. If the CUDA kernel blows up, think memory access violation, happens all the time. The only thing you're going to get back is CUDA device synchronized failed. We'll talk about how to debug that in a bit. Okay. Actually, I kind of already covered this slide. CPU only allows so many threads in a block. You partition the work into blocks. This is a blow up of what we were just talking about. Should have stepped my slides ahead. Okay. Inside the kernel, what you need to do, is you need to compute, you need to take the thread address and turn it into an address into your data. And that's basically what this line right here does. It's not in the parameter list, but you get past a variable called thread IDX and block IDX, right? And it's actually a three-dimensional block. So there's an X, Y, and Z on each of them. So you can imagine a cube of cubes, right? That's the visual model. And essentially, this is the same formula as indexing a two-dimensional array in C++, right? You take the thread index, add it to the block index, and multiply the block index by the block dimension, right? So this is essentially the same formula as a two-dimensional access in C, where you take the second variable, multiply it by the size of the first one, add them together. It's the same thing. This if statement is incredibly important. This is one of these things that took me a couple of minutes to, well, actually a couple of hours to get my head over. If the resulting index is less than the vector size, then you actually want to do some work. So remember that +1 a couple of slides back where we kind of did this ceiling function?
Yeah.
Okay. That had the effect of allocating more threads than we have data. Okay. This is what the hardware can only allocate threads in certain block sizes, right? And I think the smallest granularity of what they call a warp, I could have this slightly wrong, smallest granularity is what they call a warp, and that's 32. So if I need one thread on the GPU, I need to launch 32 of them. Mm-hmm. Okay, when I was learning this, it took me several hours to get my head around the idea of, look, I've got 1,000 processors, or I've got, well, my card's got 9,000 processors, right? Yeah. And I'm going to throw 15 of them away. Are you kidding me? Not a problem. You've got a lot of them. So one of the things you have to get your head around when doing this on the GPU, there's a certain amount of waste that happens because of scale, right? And yeah, you're going to round up. I'm going to throw X number of processors away, and they're just going to sit there idle. That's okay. For somebody who's used to doing microcontrollers, throwing anything away is no. Okay in this context. Okay.
I had a question.
Yeah.
So earlier you said that traditionally with an if statement, it will get evaluated regardless of whether the condition is true or not. So in this case, it seems like that would end up potentially writing to some memory that that maybe it shouldn't write to.
Yeah. What really happens under the covers, and I'm not. So what I'm about to say is more historical. I'm not sure quite how this works in the SIMT world. I think in the SIMT world, the program counter just jumps ahead, right? What actually used to happen in the SIMD world is, along with your program counter, there was another bit that got tracked that said, realize this operation or not. I'm not sure if it exactly implemented that way, but that's the conceptual model. So in the older processors, what would happen is you'd say if index less than vector size, right? And keep in mind, I've got thousands of these things running, right? If this statement was true, that tracking bit would be set to 1 and the results would be realized. If this statement was false, that tracking bit would be set to 0 and the results would be thrown away.
So it wouldn't actually get written to.
It wouldn't actually get written, exactly. And keep in mind, under the covers, there's a lot of machinery to make that work, right? I'm grossly simplifying that.
Would it potentially make it faster to over allocate your results vector so that you would
can.
the statement? Okay.
Yeah, and your question gets into how the caching and memory access schemes work. If you get into this a little deeper, not only over allocating, but grossly padding your data. And I do mean grossly, like by a K of data or more, right? Actually can impact your performance and improve it, which is not what we're used to. Yeah, I get that part gets wild. Okay, I want to go hit these function annotations one more time. Global, device, and host. That's the full set of them. What's really happening here is you're telling that both compilers not only where to instantiate the code, right, but how to run the code, right, or where the code will be called from. So global runs on the GPU. It can be called from either the CPU or the GPU, right? Device runs on the GPU. It's called from the GPU. Host runs on the CPU, called from the CPU. And you can specify all 3 of these in one line if you want to. So that gives you all the combinations. It's a little counterintuitive. Okay. Each GPU thread needs to do 2 things. Identify the data elements that it's going to work on. That's basically this index calculation here, and then adding the index to the arrays that we passed in. Pretty simple, obvious offset for us. And then perform the specified work on the on those data elements. That's do Pythagorean. Okay, each kernel is invoked with variables for thread addressing. I'm going to kind of walk through this one more time. Thread index contains the contains the address of the current thread. Okay. Block index contains the address of the current block. Block dimension contains the geometry of the block sizes. So currently we're only using the X dimension. I believe initially these were probably 2D, but now they're 3D. So these under the, well, not under the covers, they're exposed to you. These are really 3D or three-dimensional values, right? Mm-hmm. So you're accessing things in 3-dimensional Cartesian space. And keep in mind, this is for games, right? And, and now physics simulations, which kind of happen in 3-dimensional physical space. So what you want to do is you want to break your problem up in this 3-dimensional space, and this is a set of tools to help you with that, right? So if you've got a volume you want to render or process in, you just simply map that volume and break it up into these little threads and blocks, and CUDA will just deal with the rest of it for you, of getting it onto the hardware and dealing with it and keeping them in the right order. And I haven't gotten into it yet. There are ways for blocks to access data in other blocks. Like if you're doing finite element analysis, adjacent cells transitioning the bounds and things like that. We'll come back to the talk CUDA with a PhD when I get one. Okay. Yeah. And we already talked about there may be more thread addresses than data. You just mask it out with an if. Okay, this is probably the hardest piece of this. What you'll find is when you get into CUDA, you're going to get this thread addressing and mapping wrong. What will happen, just like in C when you get it wrong, you will come back and get an access violation and you get to go find it. Right? Same thing, different setup. Okay, the key, this is kind of the key slide of the whole presentation, so I want to spend a little bit of time on this. The person left, but the reason I set up the data, passing it to the CPU function with pointers is because of this slide. This is basically the map showing you how to take a CPU function that we would normally do with a for loop and map it onto the GPU and do it massively parallel. There's 3 key elements to this thing. The sequential for statement becomes a kernel invocation. So if you look at line 1, I grab this for statement and it becomes this block of code and fires off my kernel, right? It's almost a one-to-one mapping. Take my I, that becomes my number of threads, and just walk it right through. Okay? Step 2, the address calculations become a thread calculation. Here's those address pointers that I stuck in there that seem to be meaningless in the C world or in the C++ world. That becomes this thread calculation right there. Do Pythagorean becomes the if statement and do Pythagorean. The work function moves across basically directly, with the exception of having to add the index. Okay, yep.
Slight question on context. We start on the left and we move over to the 2 blocks on the right.
Yep.
Is the CUDA compiler doing that for you under the hood, or is this something that you write?
No, this is something that you write.
Okay.
Yeah, I'm trying to illustrate how you would conceptually go from a single-threaded CPU function to a CUDA massively parallel structure. So think of this almost like a design pattern. Now, that said, I bet if somebody was really clever, they could write a macro or a template to do this. Where's Eric? Eric, Niebler, where are you? I may pester him for the October talk. We'll see. If you're listening, Eric, I'm coming for you. Okay. Maybe our C++ community is getting a little too small. Okay. Anyway, once you get familiar with this technique, you can generally apply it in about 30 to 60 minutes. Faster if you tend to start writing your code this way to begin with. This is kind of the key takeaway from this talk right here. It's once you get this pattern down, it's pretty straightforward to use. It is a fairly narrow use case, right? But it's really, really common. So this will let you get into doing stuff with CUDA and getting some benefit with not a whole lot of work. Okay, verification. Okay, this is meaningless if it doesn't work right. Basically, all I do for this, the verification member function is take my 2 resulting vectors and just say, are they equal? Verification results stood equal, CPU begin, CPU end, GPU result begin, and return the result. Again, really, really simple. You normally don't need to include it, but, especially if you're doing stuff you really want, to make sure is right for, financial calculations or, flying rockets or something like that. Probably good to double check. A video game, if somebody bumps into a wall a pixel early, it's probably not going to hurt. Okay, the results. So for my particular architecture, the 4080 is compute capability 8.9. That's the current, well, as of the time of the writing, it's the current one. The 5000 series are starting to come out, and they're talking about them, so that's going to get bumped. I have 76 multiprocessors and 128 CUDA cores. 128 CUDA cores per multiprocessor, right? So this is telling you a little bit about the geometry. And if you multiply those together, it's 9,728 CUDA cores, right? So in principle, I can launch 9,728 threads simultaneously. Max threads per multiprocessor is 1536. Max threads per block is 1,024, right? And if you go through that math, I don't think it works out quite exactly, but you can kind of see how things get divvied up into the blocks and threads and so forth. The CPU compute. So this is a couple of benchmarks here. The CPU compute took roughly 10,000 microseconds. The GPU took roughly 2,000 microseconds. So if I divide those numbers, for this work, I got a roughly 50 times speed up. Again, this is one case. You clearly want to do this a couple of times, right? This is just a rough benchmark. Let me state a 50 times speed up in CUDA world. It's not bad, but it's not great, right? When I look at commercial libraries and so forth, the FFT library just happened to be one that I was doing a fair amount of work with for some other work I was doing. It was typically getting speedups of about 100 to 200x on this particular hardware. So that's not bad. And an FFT does not necessarily map really well to the CUDA architecture or the hardware architecture. Getting speedups of 1,000 is pretty reasonable. If for a reasonable amount of work, you're getting a speed up of 1,000 when I've got 10,000 cores. Okay, for talking CPU land, that's not great. That's highly sublinear, right? But because of the overhead and the architecture things, and so, that's pretty reasonable. If you really want your last every ounce, you can probably push it up to 5,000 or so for almost 2-to-1 type speedups, depending on how hard you want to work at it. How hard do you want to work? How hard do you want your GPU working? It's a trade-off. Okay. Yeah. Okay. So not a great speed up, but for 30 minutes of work, not bad. Okay, let's talk about debugging. And I've got 18 minutes or 28 minutes left. 18 minutes left, 17 minutes left. Okay, debugging CUDA kernels is a bit more challenging due to the following issues. First off, there's thousands of them, not just one. There's a lot of them, right? How do you keep track of these things? Second, the access to the GPU memory is more restricted. I don't know how many folks have done like debugging on DSPs or something where you've got some type of coprocessor running. You've got the same problem here. A couple guidelines to get you started. Put the work to be done in a function, just like I did here. Call that same function from both places, okay? Now you just simply debug your work function in a single-threaded, simple, familiar environment. Get all your math working, get all your test cases working. Do that on the CPU, right? Then move it on to the GPU. Once you've done that, all you have to debug is the data mapping, right? You've already got the algorithm sorted out. And you've already found all your edge cases and weird things like that in an environment you can run one of them and have good control over. All you have to mess with is the data mapping, and that's enough, okay? Until you get used to it, the data mapping will bite you. And until you get your head around how you debug it, you're going to go find a wall, beat your head against it a few times, and then realize, oh, that's the way you do this. It's not hard, it's just another way of doing things. A couple of hints for how to do that. First one is reduce all these thousands of processes and threads running to just one. And you do that by simply function one and send 1, 1 as your geometry, right? Nothing saying you, just because you have, thousands of threads capable, you don't have to use all of them, right? Especially when you're debugging. If you put in just 1,1, that will just take your first data element. And once you've got that working, the first data element ran and at least the start of your data mapping is correct, right? It also means on the GPU, when you set a breakpoint or do a printf, there's one of them, not 1,000 of them, right? Okay, and it turns out that'll get you a good step. Next thing to do is make it a little more complicated. Run it with 1,2. Now there's 2 of them running. Okay, what you're doing is you're very systematically walking through the edge cases of your data mapping. I've got the start of the data mapping working, right? I've got the index to go to the next element working. Okay. What's the last thing I've got to debug?
The end.
The end. I've got the start, I've got the step, I've got the end. The only place the end shows up is in that if statement. So now you can, at least for this simple example, those tools let you take it apart and work each one individually and not just get a memory access violation. Where'd that come from? I have no idea. This is how you take it apart.
Weren't you saying earlier that there is a modulo 32 or modulo block number? So even if you do 1,1, don't you end up with?
It's going to launch 30. Yeah, it's going to launch 32 processes.
That is,
or 32 threads, I should say. It's going to launch a minimum.
Past the if.
But there's only one of, it's going to launch it against a minimum of 32, right? Whatever that.
So there's still that confusion potentially that where you cannot.
The tools will actually mask all that out for you.
Oh.
So when it launches against all the rest of them, if it doesn't really need them, basically the others just kind of go hang in the background, right? So I've only asked for 1. It's going to just, the rest of them, they kind of magically disappear. Now, the key is though, when I do that, the +1, when I'm, counting how many I need to launch, that one I have to deal with myself, right?
Yeah.
So I've got to deal with the garbage extra at the end of my data arrays. That one I got to deal with, but the CUDA will deal with that last piece for you. The other thing you can do to even get this a little better, guess what? If you're in Visual Studio, and I'm going to say this only for Visual Studio because I haven't done anywhere else yet, printf works just like you expect it to. So I can go into my CUDA kernel, I can say printf, and guess it does exactly what you expect it does. If I'm also running 1,000 kernels, guess what? It does exactly what you expect it does, 1,000 times. Not helpful. Okay. If you're in Visual Studio, breakpoints and all the visual debugging techniques work just like you expect them to, with one exception. Instead of launching the Visual Studio debugger, you go into this extensions menu item, say Nsight, and start the CUDA debugger. The CUDA debugger is also smart enough to walk from the CPU to across the GPU boundary. So the one debugger will handle both.
So you can single step.
You can single step, you can hover over things and see values. Everything you can do in Visual Studio land basically works in CUDA land. There is a caveat. And for folks who have done remote debugging on heterogeneous systems, like using, GDB or something on an ARM processor from a Linux workstation or something like that, all the usual caveats apply. You are stepping across a processor architecture. There's inherent weirdnesses about that. Same type of weirdness, code is optimized or not optimized. There's inherent weirdness about that. So caveats apply. Got 10 minutes left. Additional resources. This talk has barely scratched the surface of what can be done. People can spend their entire careers doing this. Some do. This was a very simple problem, just getting you started. The CUDA main documentation is listed there, the development tools and the thrust library. That will pretty much get you everything you need to know around this particular code example from the official documentation. There's two really good books that I read related to this. Programming in Parallel with CUDA by Richard Anderson, and Programming Massively Parallel Processors by, I'm not even going to try to pronounce that first name, Kirk and Josh. Both of those are really good. The Programming Massively Parallel Processors, as I remember it, is much better for getting your head around going from a small number of threads to a large number of threads, right? How do you fabricate or decompose a problem like that? And then Programming in Parallel with CUDA starts getting into all the CUDA architecture issues and optimizing for your hardware. And if you think hyper-threading on a Intel processor is wild, where you suspend one process and wait for the memory to come while you run another process. Just a little nugget for you. CUDA can do that to 16 levels deep or more. Okay, it grabs these huge swaths of memory and then just parcels them out. And I still haven't quite got my head wrapped around that yet. This is what you will see though, is this is one of the things that really gets in the cheaper gaming CPUs, like the GeForce series. So the 4080, 4090, 4060, that series, versus the professional CPUs, A100, H100, that, so the gaming CPUs start from a couple $100, and I think I don't know what the 4090 is now, $1,500 or $2,200. So, that's, cost of entry is not too bad, because you can get like a 4050 for like 250 or something. Double check prices on that. Those are old and off the top of my head. For reference, the big boy CPUs are $30,000 and $40,000 a pop, right? And you can't get them because Mr. Musk and Meta and Amazon and everybody and OpenAI are sucking those up like faster than they can be produced. Go get a gaming GPU. It's good enough for most work. Finally, shader toy. It's really good for getting your head around this thread addressing and doing it in a graphical way that's visual, and at least that worked for me. We have 7 minutes left. Questions?
First question, I'll let somebody else have the next question before I bring up my second question.
Okay.
You talked about the NVIDIA GPUs, but they're not the only makers of GPUs. Do you use the same APIs for others, or is it different for each one?
No, CUDA is NVIDIA specific.
Okay.
So AMD, and I can't remember what theirs are called.
Rockin'.
Okay. They have their own version of CUDA. If you want to write things or applications that span multiple GPU architectures, you want to start looking at things like OpenMP and SYCL. We've had a couple SYCL talks here. Basically, there's abstraction layers that build on top of the lower level APIs, and you want to sit up there. And of course, that comes with a small performance hit.
Yeah, I just want to mention now OpenAI is joining the race with Triton, because they're general GPU programming API.
Oh, okay. By the way, there is one more about.
It's in development. It's called Triton, Triton.
Oh, okay. I haven't seen that one yet. By the way, there is another. I didn't get into it in this talk. There is also NVIDIA has a TPU on their system, tensor processing units. Those are there. There is a separate API to deal with those. But if you're using the libraries, the CUDA libraries like CUFFT, CU BLAS, and stuff like that, it will actually target the tensor processing unit for you when appropriate.
Yes.
And so that was one of the things you know, if you're using the, the higher level libraries and not going against the hardware directly, you still need to do some of this stuff to know how to move things across and do simple work. But once you get those higher level libraries, it will target all of the dedicated hardware for you or specialized hardware pretty much automatically. And you can pick up that gain without having to be a PhD either.
Are the QBLAS and QFFT libraries, are those like provided by NVIDIA or by the community?
NVIDIA.
NVIDIA, okay.
Mm-hmm. Yeah, and I haven't used the CUBLAS, I've used CUFFT, and it's pretty straightforward to use. I mean, as straightforward as any FFT library is going to be. Okay, other questions? Do we have anybody online that's got a question? I've been my apologies, I've been really bad because I've been looking at the room and not the camera most of the time, so. I've got
Hey, Lloyd?
Yeah.
Quick question. I know there's no simple answer, but I'd like your thoughts if you've got an application where you think might have, you might want to use the GPU for. What kind of, what are your thoughts on regular CPU threads, stood threads versus all the extra work to go to the GPU?
I think it really depends on your application. I mean, if you've got, go back to. Go back to this slide. If you have a data pattern that fits this use case, you're probably better off on the GPU. If it doesn't fit that use case, you're probably better off on the CPU. Okay, we got about 3 minutes, probably enough time for one more question before we get out of here and let Anna go home.
So I'll ask my second question then. So you mentioned there's going to be a few wasted GPUs at the end, and that the results for those are just thrown away.
Yep.
That's good, but what if the results from those result in a memory access error? Because you're trying to pass in a data or an address of data that you haven't created data at that address yet. Does it just ignore that error silently, or does the program still default?
No, so that's basically that if statement in there. Mm-hmm. So it's up to you to truncate that access and just not do those memory accesses when inappropriate.
Okay, so you're passing in bad addresses, but you're protecting against some of the if that you showed us.
Yep, and there's actually two ways to deal with that. And I'm not sure which way is better. One way is basically what I showed here with I'm not going to chase for it, but with the if statement. The other thing you can do is simply pad your arrays out so that they're the full length and then just let it go. I don't know which way is better, and it may be application specific. Okay, we got 2 minutes. Thank you all for attending. We'll be back next month. By the way, I cannot remember who's doing it. I think, is it you doing? We do have another CUDA talk coming this year.
No.
It's not you?
Not me.
Okay. I think, I don't remember if it might be next month. I've got to go check my email. There was two of us talking about doing a similar talk, and what we did is I did a intro talk, and whoever the next person is who I cannot remember is going to do a slightly more advanced talk. So if you're into this topic, we'll see you in about another month or so.
Cool. Thank you.
Thanks.
Yep.
Thank you.
All right. And it's now 8 o'clock, so I need to switch from speaker to cat herder and get everybody else so Anna can go home. And there's the cat. No.
You taking a look at standard SIMD, the proposal?
No, I have not looked at that yet.
Okay, yeah, I was just wondering if you had seen it, how you thought it might compare, but if you haven't looked at it.
I haven't looked at that one.
It does.
I did somewhat do something
I was actually going to talk about maybe doing a talk in October.
Okay, yeah, just send me a note. I'm looking for an October speaker, so if you happen to have one, do you want the slot for sure, or are you still kind of thinking about it?
So I had a talk that I was going to give at an audio programmer meetup.
Okay.
Might work well here also, but
Yeah,
it's a bit more C++ heavy. So if you're looking for something more exotic,
yeah, go for it. That's,
well, I was also thinking about doing talks about the Jive program.
oh, that would be cool too.
If
Yeah,
that seems more interesting, I'd be happy to do that instead.
whichever works for you. I'm happy with either one.
Yeah, well, I'll send you an email then.
Okay.
Work it out. Yeah. Awesome. Yeah, I really like the talk. This was a lot of fun.
Oh, thank you.